Thanks, Chairman, Professor Chen. And good afternoon, ladies and gentlemen. It's my honor to present our research result here this afternoon. I know this is the last talk of the conference, so I always remember the main duty for the last speaker is to close his talk on time. So I will remember this. Okay. In today's conference, we learned a lot of case study. But right now, I'd like to present the material based on research result of the last few years, funded by Water and Soil Conservation Bureau and the Central Geology Survey. And my topic is monitoring and analysis of large-scale landslide mobility in regional scale. Actually, I'm talking about the whole Taiwan through how do we working for the monitoring deep city landslide. Okay, if we look the Taiwan area or Taiwan Island, we know severe landslide usually triggering by earthquake or typhoon. And during Typhoon Morak in 2009, there is a Shaolin landslide caused 450 casualties in this event. And after this event, we start to pay attention to deep city landslide, actually. Before Shaolin landslide, we know deep city landslide, but not too many people pay attention to this kind of phenomena in the island. And fortunately, we have the LiDAR DEM taken in 2005 in this area. So that's the 3D view of LiDAR DEM taken in 2005. And that's the event after Shaolin landslide. We see the aerial photo. Compare these two, and we really identify or study the morphostructural phenomena. We see, actually, we can see some moving signature of Shaolin landslide before it occurred. So, during the same time after Shaolin landslide, the government of Taiwan initiated a nationwide LiDAR mapping project to construct 1 meter resolution DEM through the whole island. So one of the main purposes of this project is try to identify the potential site for catastrophic landslide or large-scale landslide. And at the same time, in the Taiwan, we define the large-scale landslide. The definition of the large-scale landslide mainly concern the magnitude of hazard. So it may differ from the Western people used. But here, we mention the large-scale landslide should involve a large debris volume when it fails, and also may have a deeper sliding surface and include fast failure movement, and also involve bedrock deformation. So, at the same time, after Shaolin landslide, we compare the morphostructure in Qishan River watershed. The area is covered about 650 kilometers square. And we identify 261 deep city landslide in this study area. And compared to the landslide occurred during Typhoon Morak in 2009, we found 53 landslides with the area over 10 hectares occur within the same study area. So, in the same study area, using the 2005 DEM, we can identify 261 deep city landslide. And during event of Typhoon Morak, 53 landslide with the area over 10 hectares occur. And all these 53 fall within the 261 deep city landslide we identify. So that's the key problem we believe. A lot of large-scale landslide transform from deep city landslide. So that's the reason if we would like to identify the location of the large-scale landslide, we need first to identify location of deep city landslide. That's all the approach first we try to do. So I show one example. That's the 3D aerial photo at Namasha of Kaohsiung County. And very difficult to look or identify deep city landslide. However, using LiDAR DEM, we can see the morphotectonic structure, and it's quite clear to identify the boundary of deep city landslide. So, using this kind of information, and by using 1 meter resolution LiDAR DEM, we constructed after 2010, and so far we identified 90 to 30 deep city landslide through the whole island. So actually the number is over 9,000 of deep city landslide have been identified. The problem is after we know so many deep city landslide, what we can do is tough to make a decision to select which we should pay attention to. I think that's the problem. And within a short time, like within 4 years, the government tried to establish hazard mitigation program for deep city landslide. After we know so many deep city landslide, what we can do? So I think we selected some important sites to make a monitoring or for detailed investigation. That's the first step. And we consider the damage or historic hazard, and also consider variability, susceptibility, and the activity of deep city landslide. So within 9230 site, first, with regarding to the variability, the Soil and Water Conservation Bureau selected 182 sites for detailed study or monitoring. Among 182 sites, if it shows damage phenomena or have a historic hazard, let go directly go to detailed investigation. Otherwise, if they have a moderate to high variability and also with high susceptibility, then we also go direct to the detailed investigation for this site. In the other situation, if they have the moderate to high variability, but also only with low susceptibility, but using the INSAR information, we evaluate they have the moderate to high activity, then we install real-time GPS monitoring system. And for susceptibility is moderate, and we also select site to install real-time GPS system. After we collect enough information from GPS data, if it's really active, then we will working for detailed investigation. That's the philosophy or approach we work right now. From 90 to 30 sites, we try to select 34 sites to install real-time GPS monitoring system. And so far, we finished 23 sites already. And for only 182 sites, we are using INSAR technique to monitoring their activity. So next, I will show basically how do we estimate the vulnerability. We need to know the area influenced by landslide, large-scale landslide if they fail. So within a short time, we need using some empirical experience. We don't have time to make a detailed study. So we choosing the Japanese approach and supported by some organized institute. If we identify the area of the potential or deep city landslide, then we including 30-meter wide buffer zone. That's the potential sliding area, using the flip approach and try to identify the possible deposit area. So it's a very simple approach because we have over 9,000 sites need to work for this. So we're using a very simple approach. estimate the area we are affected by large-scale landslide when it fails. And after we know the area, then we can calculate the vulnerability. So that's the first approach. We try to estimate the vulnerability of each landslide. The second one, the susceptibility. Okay, I just mentioned we are lucky we have a 1 meter resolution LiDAR DEM taken in some part of Taiwan in 2005. Using this kind of information compared to the large-scale landslide inventory map induced by Typhoon Morak, that we only using that event. And we try to, using the weight of evidence method, to calculate the susceptibility of each deep-seated landslide. And we know it will not really represent the susceptibility if we have much more detailed information. But don't forget that we have 9,000 sites. And within 4 years, we try to establish a preliminary hazard mitigation program for the government. So that's the approach we did. And we consider 5 affecting factors, including slope gradient, distance to river channel, lithology, distance, type of slope, and the distance to geological structure. And using the data, the landslide inventory map consider the landslide only with the area over 10 acres occurred during Typhoon Morak as the sample, and assume all this landslide is transformed from deep-seated landslide. And using the deep-seated landslide, we identified in 2010 the sample 2, and to calculate the weighting of each factor. So, using these two approaches, that's the distribution of the 9,000 sites in Taiwan, and that's the 182 sites distributed in Taiwan. We select for annual deformation. For 182 sites, we using INSA technique, monitoring their activity, and we work every year. And for GPS install monitoring system, it will be near real time. So we can collect the data all the times. So now I show you one example. We using actually for the INSA information. We using JASA, AROS, and AROS2 data. The reason we choose AROS and AROS2 data because they are L-band images, and the L-band with longer wavelengths have better penetration capacity ability to forest. So under the heavy forest environment, you are experienced using L-band data, we will get a better result. And the technique for the INSA analysis, we using a modified short baseline INSA approach, which we call temporary coherence point. It's done by co-author of Lo Fei Chen and from Chinese Cultural University. The result, I will choosing the changing area, show you some of the result. The data we use, that's the result of AROS image from the images taken from 2006 to 2011. And the result of the changing area, like the screen here. Like previous author mentioned, the information of the INSA data is in the light of sight compared to the satellite. So in this case, for the east-facing or south-facing slope, the blue color represents the area moving down slope. The yellow or orange color represent the area moving upward. The reason we see moving upward and moving downslope for the upward, because don't forget, the island of Taiwan is located active mountain building process. So uplifting is still going. However, for the moving downward, we believe that's related to the movement of a deep sea landslide. And if we look detail of the changing area, and first we see we using the LiDAR DEM to identify location of deep sea landslide. Then we superpose the result of the INSAR information. And the result of INSAR information is consistent with the area we identify from 1 meter resolution LiDAR DEM. The result is quite good if we make comparison. And if we make comparison with the GPS information nearby the study area, that's the Meifeng, that's the Lushan, and we see the magnitude of the TCP INSAR is quite consistent with the data we're recording from GPS. So we think this kind of information is believable. Okay, that's first. We're using the INSAR technique to get annual displacement rate of our study site. In addition, if we look detail of one specific site, that's the D057, that's the boundary identified from LiDAR information, and some morphostructure we put, and that's the result of the TCP INSAR. And using TCP INSAR also can help us improve our interpretation. So for the example, in this slope, the deep sea landslide should put the boundary a little bit more to here. That's if we compare the INSAR information, they can help us to modify our interpretation of LiDAR DEM. Okay. Besides the annual displacement rate, using MT technique, we also can get incremental deformation of two consecutive images. So in this case, the result of TCP INSAR of this image cover Typhoon Morak event. In this case, that's the other result cover Typhoon Kameji event. From these two data, we can see within a deep sea landslide, we can identify two active moving blocks. One is this one, the red color, white color represents displacement rate is very high compared to pink or green. So the white color here represents the block moving fast. So during the Typhoon Morak event, within this deep sea landslide, we can identify two active moving blocks. One is this one, the other one is this one. And similar to Typhoon Kameji, and we see this one has much more displacement moving downward, and also this one. These two are consistent. So we think using the TCP INSAR also can help us to identify active moving block within the deep sea landslide. Okay, that's the first one. We're using this kind of technique to monitoring 182 site we select. After that, for site, we install single frequency GPS monitoring system. The reason we're choosing single frequency GPS because it's cheaper. And for landslide monitoring, the space baseline only 1 to 2 kilometers long, so it will be okay for single frequency GPS to calculate the displacement. And for each site, we install 6 GPS stations, one for conference, the other 5 is installed within the deep city landslide. And we also have 1 rainfall gauge and 1 extension meter. This kind of recording data, we calculate every hour or every day. So they can give us a 1-hour resolution solution or daily solution displacement. And all the data is real-time transformed to our server, and they can make calculation every hour or every day. And I'm using the site of D021 to illustrate how to work for the GPS displacement system. And for this site, we put, let me see. We put 5 GPS within the site of a deep city landslide. And we can recording the data. Here, the resolution is millimeter, so that we get at least centimeter resolution displacement for GPS data. And actually for horizontal direction, it can be reached to millimeter level. But for vertical displacement, it's a centimeter. Okay, so that's the case of Taidong D021. And during some heavy rainfall event, and we can see the displacement. And we can really catch the displacement almost near time. And in this case, we also see the creeping behavior in some case, even without the heavy rainfall, but we see creeping of the surface. The problem is using GPS, we don't know. It's really displacement or movement along the sliding surface or just surface process. So, but using these two kind of approach, we try to catch the surface deformation. And after we have enough surface deformation, ideally, we should have further study using subsurface data or instrument or borehole to have much more information to understand kinematic and the mechanic of the movement of the deep city landslide. So that's the approach we're using through the whole island so far. So my conclusion is we try to select some important target to study or for deep city header mitigation. And over 9,000 deep city landslide. And we select 182, only consider the vulnerability. And within the 182, using INSA technique to monitor their activity, and using the philosophy we just mentioned, and we will select 34 sites to install surface monitoring system. But so far, we only have 23, and we have 10 more should be installed in next 2 years. And after we have enough information, we try to combine with the data of Professor Xie and the government will try to get the triggering threshold. I think that's including the rainfall, maybe including the displacement, and we also have the almost the real-time monitoring system and try to have the evacuation system in next 2 years. I think that's my talk. Thank you very much.